time for everything. What I bring you today here is a machine learning stack for predictive and prescriptive analytics. The context of everything developed for this project is based on machine learning operations, also known as MLOps. People may think that a machine learning model can be developed and continue operating forever. However, like every machine, they need to be continuously monitored and maintained over time to see how they are performing and shifting with new data. This is where MLOps comes into action. It can be seen as something similar to DevOps, but in the context of machine learning. So basically, MLOps allows to deploy, monitor, and manage machine learning models in production at scale in a reliable and efficient way. Many companies are increasingly adopting this concept since it allows them to leverage the benefits of machine learning in the real world, allowing fast innovations through a robust machine learning lifecycle management. It works like a bridge between data science and operations teams, as well as other teams, improving their collaboration with each other. MLOps also keeps track of version history of models and also their performance to enable auditing and allow a faster intervention when models start to degrade. The purpose of my internship was to come up with a flexible machine learning stack that handles big quantities of data and that processes it in both streaming and batch. This is the basis of a project being developed for Zeugma and Siemens. The main goal was to define technologies for the database, for data flow management, and for MLOps. However, there are a huge amount of technologies, so the task for deciding each technology should be chosen, it's not that easy. Just in this image, there are a big amount of technologies, but only for concerning machine learning and artificial intelligence. So trying to find this huge amount of technologies, it should be hard. But after some research and analyzing some advantages and disadvantages of those technologies, we came up with this first approach, using these 4 different technologies. We can start with Kafka, that is a distributed event streaming platform consisting of servers and clients that communicate via TCP, and it is used in the project to process stream data before they go into the pipelines. The next one is MLflow, which keeps track of the models by logging parameters, versions, metrics, and other relevant information that might be useful to the user. Airflow consists of a platform to schedule and monitor workflows, and it looked like a dynamic and scalable option to manage machine learning algorithms and the part of MLOps of the project. Lastly, we have MongoDB. That is a NoSQL database with high flexibility since it saves data in JSON files. And this way, we can have small changes in the data structure that don't compromise all the system. In this project, we used the community version of Mongo. Having all the technologies decided, I started developing some actual pipelines with a model and data from another project of the lab that was only used to validate the structure. And what happened with this stack was that the pipeline's tasks took too long to be allocated and executed. It could take like several minutes from the moment the pipeline started until it was finished. So it was obvious that this wasn't the perfect solution if we wanted to have a stack that was able to stream data and obtain an output as fast as possible. Analyzing the current technologies, every platform seemed to do what they were expected to do without any problems except for Airflow, which was responsible for the high expense of time. Airflow is not made to deal with streaming data, so it is not its main goal to make everything run as fast as possible, but more to make sure that the tasks are done and they are done in a specific order. Besides that, it also doesn't allow event-driven pipelines or streaming, and it wasn't also fond of passing data from one task to another, which can be useful for our case. For all those reasons, new platforms were searched to try to replace or at least complement Airflow. In this table are presented some of those platforms that were found and could be interesting to do that job. To help better understand those characteristics, I tried to check the presence of the most valuable features for our projects, like streaming, event-driven, cron jobs. And the language, the preferred was Python, since it was an easy and well-known language. And the pipelines that were already developed in Airflow were in Python. So if we kept the language, it would be, we could reuse the code and we could save some time. For a lot of these platforms, it was hard to realize if they had what we needed without really testing them. However, there were too many to analyze and test. So I only tried to look and understand if there was any that was worth trying to at least test. And in the end, the one that looked more promising was Prefect. Prefect can be seen as an improvement over Airflow. It is also a workflow management system to control pipelines. It also allows to schedule through cron job and other ways and trigger pipelines. But unlike Airflow, it has a much faster allocating system that allows a faster processing of the pipelines. For this reason, we stayed with this platform and tested it out with success. Although most of our needs were met, the stack still didn't allow data streaming. So after some research, we found the platform Faust to try to suppress that need. What Faust does is to listen to Kafka topics, and whenever the data arrives, it processes it the way we want. In this case, what it does is to trigger the pipeline corresponding to the topic in which the sample arrived. Imperfect then implemented 3 different pipelines. The first one is a predictive pipeline to detect if a failure in a machine is going to happen or not. The second pipeline is for optimization, which is triggered every time the prediction results in a failure, and returns a recommendation of which variables should be changed to avoid the failure state. Like, for example, it could recommend to decrease the temperature by 2 degrees. The last pipeline is responsible for saving everything it receives in the database. It includes the original sample and the outputs from the other pipelines. It should be noted that the database has no defined structure yet, and the data is being kept in tables corresponding to the origin of that data. That means if the data comes from the prediction pipeline as the output of that pipeline, it is saved in the table for that pipeline for now. Now, we will see how those technologies that we talked about communicate with each other. For each pipeline that we already talked about, there is a different topic associated. Since this way of organizing the topics, it makes it easier to know to which pipeline should the samples be sent to. Whenever a Kafka topic receives data, Faust acknowledges it and triggers the corresponding prefect flow. Other relevant information from the pipelines can also be logged into MLflow, like the outcome of the prescriptive analysis or the predictive analysis. So now I'm going to make a little demonstration. Let me just change the screen. So we have two main UI interfaces for our system. There's one for MLflow and another for prefects. The MLflow, as you can see here, has the records for each run that we track, for each moment that we decided to track. And for example, in this record, we can see different metrics for the resulted from the prescriptive pipeline. That means the optimization pipeline, and there are a lot of things that could also be tracked with MLflow. When we're seeing the prefect interface, we can see here the history of runs that were made, also other summaries, and here we have all the flows that we already talked about. If we go into one flow, we can also see the run history. There were 2 an hour ago, and the other summaries correspond to this flow. If we select a specific run, we can see the tasks that were completed and which one failed, if that was the case, and also check the logs, that the prints that are made in the program during the flow run. So other features that this interface has is to, if we go to a flow, we can run it from here immediately. But in this case, it doesn't really make sense since we don't have data receiving. And we can also schedule it for a specific time or for 5 minutes or something like that. I can show you how. This is a script to send a sample data to the topic A. That means to the prediction flow and to the database flow. So we can see here the two flows that were triggered by that script, and after some time it will be completed. We can also, if we wanted to create a new pipeline, we could do. We just have to write this line with the correspondent name of flow that we want, and inside of this we can do whatever we want. We can call the tasks that we want. That is basically a function with a tag task, and in the end we have to register it in our project, so it appears on the interface. Let's say now that we want to have a Kafka topic associated with this flow. We have two ways of doing it. We can come to Docker Compose and have here another topic, but this won't work if our system is already running. So if it is already running, we have a command that tells the Docker to create that topic. However, if we stop our system, if we stop the Docker, we will lose that topic, and if we don't put it here it will be lost and we have to add it manually again. If we want to, for this topic, to trigger that pipeline that we created, we can come to the script that corresponds to the FOST and have another agent that will be listening to this topic and trigger the flow that has the name we gave previously. Okay, so now going back here to our presentation, sorry. Let me just changes. Okay, so now we are here, and as the time for development was not that long, and as there is always some space for improvement, there are some points that could be done in the future, and they are presented here without any particular order. One of them is to implement and explore ways to detect concept drifts, that is, to detect when the distribution of the streaming data changes and starts classifying more times wrong than right, which can easily happen with this kind of data and can happen for various reasons. Whenever these drifts are detected, the model should be retrained with the samples that were retrieved until that moment. And for this, a new pipeline can be developed and triggered when there is a drift. Scikit Multiflow is a platform that allows to easily generate data streams from a given dataset and even induce concept drifts. So that would be interesting to implement in our project to see how would the system respond to that drift and just normal data. Lastly, until now, the database structure is not well defined because it can vary from project to project, and we still didn't have access to the data that will be used for this project. So this is a point that should be done when the access to that data is given. We're still looking at the database. A REST API can be useful to access the data from outside of our stack, and it should be explored if already exists one for MongoDB. Otherwise, it should be created a new one from scratch. So this is all for my presentation. Thank you so much for your attention, and thank you so much to everybody in the lab that helped me throughout these months. And yeah.